Can I use this mic? Yeah, okay. Wonderful. Okay. Hi, everybody. My name's Mario, and I'm here to tell you about one of the many projects that are going on inside Huawei research concerning effect handlers. If I may, let me start this talk with a quote by Guy Steele. I'm not sure I'm senior enough to be the kind of person that starts talks with a quote by a famous computer scientist. But I quite like this one. We were not out to win over the Lisp programmers. We were after the C++ programmers. We managed to drag a lot of them about halfway to Lisp. And so this is partly as an excuse for perpetrating Java. Now, I would like to start this talk with a slightly modified version of this quote. We're not out to win the Coca programmers. We're out to win the C++, or very specifically the C programmers. And we hope to manage to drag a lot of them halfway to Coca. The first question that you're forced to answer is, why would you do such a thing? Effect handlers, as many in the audience might already know, are an incredibly expressive programming language feature. They generalize stuff like green threads, actors, generators, exceptions. They can basically implement any sort of control flow that you want. And it turns out that there's only one programming language in common use today that lacks every single one of these features, and that's C. And so it stands to reason that C programmers have actually the most to gain from introducing effect handlers to C. But in a more practical sense, what happens at Huawei is that we have tons of people working on C, especially in embedded contexts. We have lots of people using C to write firmware for telephone switching hardware. We have lots of C that's running right now in data centers inside embedded devices. And one thing that happens a lot, and we actually see this a lot, is that there's a proliferation inside Huawei of concurrency libraries. It seems that every other team is reinventing their own library for green threads, or their own library for asynchronous tasks, or their own library for actors. And so we really wanted to find a single abstraction that unifies all of these things, that we can package as a library and give it to all of our embedded C programmers and tell them, look, here's the one thing you need. All of the stuff that you've been doing so far can be done in a much neater package with a much neater API with this library. And so the core audience of this library is C programmers, and specifically embedded C programmers, and that comes with a lot of very, very hard constraints. The first is whatever we come up with, whatever we give them, it has to be 100% compatible with the C programming conventions, and this, among other things, this means that, for example, we cannot move stacks around, which is, as we'll see later, it's a common approach when implementing effect handlers, stack copying. This is completely out of the question because a lot of C programs depend on pointers into the stack remaining stable across function calls. They should also be ergonomic to use by hand, and C, unfortunately, is a very, very poor language. It has a very simple type system. It doesn't have polymorphism. Crucially, it doesn't have closures. And so it's really hard to give an API to effect handlers that doesn't depend on all of these things. So as you may know, there are already a number of libraries that accomplish something similar, and they're truly excellent libraries. Both libhandler by Dan Lyon, who is in Microsoft Research, and libmprompt by Dan Lyon and Casey Sivaramakrishnan, who also give you an API from C to use effect handlers. However, the niche of those two libraries is vastly different because they're not meant to be used directly by C programmers. They were designed and developed as backends to the Coca programming language. So they're supposed to be consumed by a compiler, not by human programmers. And this comes across in the in the decisions that they make. So for example, libhandler uses stack copying to manage resumptions, which is completely out of the question for C programmers because that's going to make half of their programs segfault. And libmprompt uses virtual memory for allocating growable stacks for your continuations. That's also out of the question because when you're working on an embedded system, you don't have an operating system, you don't have a notion of virtual memory. So we couldn't use any of these two libraries. And also, finally, and this is perhaps more of a sociological point, the APIs of both of these libraries actually are based on closures. So a handler is a closure. You handle code by bundling together a bunch of closures and executing them. And it turns out C doesn't have closures. So in order to use these libraries, you have to do a lot of closure conversion by hand. And this is not only really annoying, but it's also not type safe, and it turns out that you have to go through a lot of hoops if you want your handlers to capture mutable state. It's actually really a mess. And also, and this is a lot more subjective, we found that C programmers tend to get really, really scared when you say the word continuation. This is not a moot point. I've been in meetings where I've been told, if what you do it turns out to be equivalent to continuations, we are not using it. Continuations are this weird thing that Scheme has. Nobody knows how to program with continuations. Continuations are slow. We're not using that. And so what we decided to do is do a completely different API, a completely different reimagining of effects as something that we call handled coroutines. And the idea is you walk up to a C programmer and you tell them, I have a really nice coroutines library for you. And then you introduce, you can gradually introduce all of the cool advanced features of effect handlers as they become more comfortable with it. But crucially, if they only want to use it as a coroutine library, it is a very good coroutine library. It is really fast. It has 0 allocations. It cares about all of the things that C programmers care. And so we hope, and to an extent, we have succeeded in smuggling effect handlers into the C community through the Trojan horse of coroutines. So what does this look like in practice? Here is a very simple, effectful program using libseff. First, you define your operations using this define effect macro, which takes the name of the operation, the return type of performing that operation, and any arguments that the operation may have. Ignore this number. It'll come back to haunt us later. And then, in order to use them in a program, you simply use the perform macro, and pass it the name of the operation, and any arguments. And this, you can tell your programmers, this is actually just like a function call. It's relatively type safe insofar as C is type safe, which is to say not very, but they're used to it. And so the argument types are checked, the return type of this is checked, and from the point of view of the programmer, this looks just like a function call. It may be able to suspend. That's the trick. So this is more or less what I said. Now, what is this number here? This is just a sad necessity of life. One of the limitations of libseff is the programmer needs to provide a numerical tag for each operation that they define. And we use this for very, very fast operation dispatch. But there are some limitations. You can only define at most 64 operations in any given program. And it is the programmer's responsibility to ensure that these tags are disjoint. We are working on lifting this restriction for a new release, but it's not super easy. There's something that I would like to point out here, which is not true in other libraries for effect handlers. Here, I have an effectful function that is stack allocating an array of length 256. And it is passing the address of that stack allocated array to an effect. The only reason this is possible to do is because our stacks are stable. We make you this promise. We never, ever, ever, ever move any memory on the stack, ever, under no circumstances. Crucially, libhandler doesn't provide this to you, so if you try to write the equivalent in libhandler, it will segfault your program more or less immediately. So once you've defined your effectful code, how do you handle it? And this is the most important part. We don't really have a notion of handler. We have a notion of a coroutine. So in order to handle some effectful code, you need to turn the effectful function into a coroutine with coroutine new function, which what it does is it allocates some stack space for that function to run, some metadata, and then you can immediately resume it using the aptly called resume function. Now, here comes the difference from normal coroutines. This resume function takes an extra argument, which is a bit set of all of the operations that can be handled by yielding to this context. Which is to say, whenever the code inside this coroutine performs any of the operations contained in this bit set, the code inside the coroutine will immediately yield as the return point of resume. At that point, you get a reified command. Unlike other systems, dispatching on what command has been performed is not done by the library. It is done by a standard switch statement. So you can switch on the effect tag of the request. We provide you with this convenient case effect macro, which does the matching and the unpacking of the arguments for you. And then you can just write your normal handling codes in completely indirect style. In something like libhandler or libemprompt, all of these handler branches would need to be manually closure converted code. And this is actually really bad because closure converted code in C++ cannot close over mutable variables unless you heap allocate stuff. And if you're not a C programmer, then you don't care about this. But if you're a C programmer, you really don't like to allocate at all. Now, returning, when the code inside the coroutine returns, this actually also behaves as if it were an effect. There's a different macro, case return, which handles the case where the coroutine is terminating. You have to manually delete that, of course, because this is C. We manage our own memory. And that's it. Crucially, this handler only handles the get and put effects that we've defined in the previous slide. We can separately define a similar handler loop to handle the print effect. And the code here is relatively straightforward. And then you can just compose them by composing closures. Unfortunately, some amount of closure conversion by hand is necessary because you need to initialize a coroutine, and initializing a coroutine requires you to create a closure. So at the end of the day, you can run this piece of effectful code by wrapping it in a closure and then wrapping it in another closure that runs the handler for state and passing that to the handler for print. Okay, so far so good. Here's some information that I don't want to spend too much time in this. This is just there for reference, but this is the entire API of the coroutine lifetime. You have your functions to create a coroutine, delete a coroutine, and a couple of functions to stack allocate coroutines if you're into that kind of thing. You can perform an effect, you can yield from a coroutine, and you can resume a coroutine with a set of effects that you're willing to handle. Crucially, coroutines are also thread safe, so you can pass coroutines across threads and start them in one thread, pause them, pass them to another thread, start them on that thread. And this is actually how we achieved a work stealing scheduler that I'll show you later. If you know anything about coroutines, you know that stack handling is pretty tricky. How we deal with it is we use segmented stacks. This is relatively straightforward because Clang and GCC these days have support for segmented stacks. And for those who don't know what a segmented stack is, instead of having a contiguous block of memory be your stack, you just have a linked list. And every time a function runs out of stack space, you allocate a new link, and you use that as your new stack. Stack handling suffers a potential performance problem called the hot split problem, which is when you have a tight inner loop that calls a function, and that function happens to require more stack memory than you need. So every time you call it, you allocate a new segment, and every time you return, you deallocate it. This is widely held to be a big problem. It's the reason why Go abandoned segmented stacks. It turns out to be not a big problem for us at all, because we found a relatively sensible way of solving this. When you return from a function that has allocated a new stack segment, instead of deallocating it immediately, you just leave it unused at the end of your linked list. And when you go back, when you call that function again, that segment is still allocated, and you can simply reuse it. And as you can see in this very nice graph, whenever your inner hot split function contains at least 10 multiplications, the overhead of this hot split with stack-led recycling is basically negligible. And if your function contains fewer than 10 multiplications, then it's probably going to get inlined, and you're not going to have this problem at all. Finally, some benchmarks and comparisons with other effect-handled libraries. We install a stack of handlers up to depth k and perform 20 million commands. We've compared libseff with libhandler and libmpf. These are the two most important ones. As you can see, we are extremely competitive in the general case. If you opt into specific library-specific optimizations that you have to do by hand, then at lower depths, we are a little bit slower than libmpf and libhandler, but as you install more and more handlers, our much faster dispatch strategy tends to dominate, and we actually become much faster. We also built an asynchronous scheduler with work stealing, and used that to implement an HTTP server, mimicking the benchmark used by the OCaml effects paper. And it turns out, we actually found this quite surprising. Our scheduler is actually competitive with Hyper, which is a fairly robust Rust HTTP server. So our performance tends to be really, really good, even if you just think of this as a pure coroutines library. So let me just finish with that. In conclusion, I think there's enormous potential for effects in C. They are, if you put them in the form of coroutines, they're really easy to explain to C programmers. They more or less immediately understand the underlying programming paradigm. And crucially, there's a lot of low-hanging fruit for compiler support, both in terms of increasing type safety and doing a lot more optimizations. And this can be done by simply tweaking a C compiler a little bit. We think we can achieve a lot of benefits in this area. Segmented stacks are a necessity, but it turns out they're not such a big price to pay. So in conclusion, I hope I can convince you that actually effect handlers in C not only is not a crazy idea, it may turn out to be a really good idea. And if you're interested in this at all, you can go to that GitHub address, download this, and start playing with it right now. Thank you very much, and I think I've run a bit over time, but if you have any questions, then... Oh, okay. Yeah, so from the point of view, so we actually give you an API where you just don't see the effects at all. You have a fork function, you give it a closure and it runs it in a different thread. You have a yield function, and these are, from the point of view of the programmer, they are just regular functions. They just perform effects under the hood. And then you have a bunch of input-output operations that we provide to you as an input-output library, which are asynchronous. And underneath, they use a wait effect that basically tells the scheduler to block that thread until a certain condition is satisfied. So it actually looks a lot like a traditional async I/O with coroutines that you might have in a high-level language. You don't need to think about effects at all.
Super, thank you. So let's go. Yes, thank our speaker again.